So as Jan mentioned, I actually joined as a researcher in this group in 2014. And 2 years I struggled without any results actually, because those nanowires were not working the way they should. And then we found a lot of problems. And one problem was this electrokinetic effect, which I turned into a different solution. So that's the story I'm going to talk about. But before that, let me ask you one question. And that the question is, how effective you think our healthcare model is? How sustainable it is? Now, if you look at our healthcare model, it's very simple. It starts with a disease, and then we take a medicine and to try to kill that disease. Now, in this model, the healthcare actually begins with a sick patient. It's an irony. It's not in healthcare. It's a sick care, right? Now, the reason why this simple model has been so popular is partly because of Antibiotic Revolution, which started about roughly 100 years ago. So although it was developed for treating infectious disease, but the very simple principle in it, that you can simply take a drug and basically kill any disease, was so attractive that it swept across all sort of medicine and healthcare. Yeah? And people started to follow the same principle over and over again. Well, but we have a roadblock now, as you might know, that antibiotic resistance is going to be a menace in few years. And what you see here is 700,000 deaths per year from antibiotic resistance alone. Just imagine, these deaths were once curable, but not anymore. And this data also predicts that by 2050, at this rate, there will be 10 million deaths. So it's not only casualties from antibiotic resistance, there are tons of different diseases. For example, coronary artery disease. It causes us 7.5 million deaths. Stroke, it causes us 6.8 million deaths. Here, it's not that we don't have the drug, but we don't have the time. The point it appears, we can't really give them the drug on the right point. Now what do we do? So clearly we see that our healthcare model is going to fail, either sooner or later, right? So we need to change that. So one way to change that is that you can think of a preventive and personalized treatment. Now how do you prevent a disease from appearing? Of course, you have to make system that allows you for continuous healthcare. Not that you go to hospital for your healthcare. It will be already integrated with your daily activities. And of course, for that, you need tons of sensors. And those sensors, it can be built with electronics, optics, or fluidics. But it should be able to analyze a wide variety of biomarkers, for example, cells and exosomes, DNA, RNA, metabolites, and proteins. And finally, our objective is that if you give a drop of blood, we should be able to tell you what is going on in your body. And this is an ambition that has attracted a lot of giants. So you have probably seen Microsoft, Samsung, Google, and Apple all have healthcare devices. And they have giant labs and research facilities nowadays. Now I'm going to talk about one principle that we have developed in our lab, which can actually sense all these different varieties of biomolecules. And I'll give you a few examples. Now what is electrokinetic effect? Well, electrokinetic effect actually means a bunch of different principles, which includes electrophoresis, electroosmosis, streaming potential, and sedimentation potential. I mean, the way I planned to give this lecture was that I will draw those things on the board, but let's skip that for the moment and go to the fundamental how it works. In all these different phenomena, what we need is two phases, and there is a charge accumulation between the phase. So here it is shown with the solid and liquid. Yeah? So what leads to charge accumulation at the phase of two different phases? Well, there can be many different reasons. For example, difference in electron affinity. You have probably seen if you bring metal and semiconductor, you have these things. So you have Schottky barrier, right? But this is not responsible for solid and liquid interface. In solid and liquid interface, the charge accumulation may originate from difference in ion affinity. So in liquid, you have many different kinds of ions. And these ions can sit to one surface preferentially compared to the other surface. Or you can have you can have ionization of surface groups. As I showed, or Jan also showed in this nanowire transistor, you had silicon oxide, and if you have liquid on it, it ionizes to produce silicon hydroxide with different charge state. So you can have this kind of charge accumulation. So when you have that, so this is what is shown with the metal oxide. You have many different charge, like negative charge and positive charge and so on. And this is actually a predominant mechanism of charge formation even in biomolecules, when they are in liquid. And the net charge depends on the pH. So for example, in silicon oxide, around at 3 pH, the surface has 0 net charge. But if you go above or below with the pH, you can make it positively charged or negatively charged. Now what happens? So now I have a surface, solid surface. I have liquid. I have interface where the surface is supposed to get a lot of surface charges. But we know that the liquid might also have a lot of ions, right? Liquid may contain cations, anions. And if it is a polar liquid, it will be solvated with the liquid shell around it. And what will happen is that these ions will be attracted to the charged surface, right, to compensate for the electric field. And as a result, you have a layer full of ions and charge, which is called electric double layer. So one is solid surface, giving you negative charge in this case, and you have positive ions accumulation forming the electric double layer. Right? And the thickness is determined by this lambda d, or the Debye screening length. And here is a sort of distribution of the potential from the surface. This psi s is the surface potential. And I have defined another potential, which some of you might know, it's called a Zeta Potential, very important parameter, which is defined as the potential at the interface between the mobile layer and immobile layer. I forgot to tell you here that some of these ions, which are away from the surface, are mobile in a sense that if you apply some force, you can shift them away. But some layer, which are very close to the surface, they're so tightly bound that you cannot move them. Now, if you consider the same situation in a microfluidic channel, you will have an electric double layer close to the surface containing some mobile ions, right? And now, if I apply some flow, I simply flow the liquid through it with some pressure-driven pump. And as the liquid is viscous, it will drive some ions, some mobile ions, towards the flow direction, which will create a charge separation between the two ends of the microfluidic, right? And that was what Jan showed was causing the flow-dependent phenomena in these transistors. But when we realized that one, we thought, well, that might be a very easy way to make biosensors. Well, we simply connect the both ends of the capillary or the microfluidics, and we pump. This is the pressure drop across it. And as a function of pressure, which is a linear dependence, you see increase in current. But the important thing is that this current has its origin in the charge distribution here. So if you can change the charge distribution, you can change the current, right? So that gives us very nice system for biosensing, which simply put our antibodies on the surface, and when biomolecule binds, we simply see a change in the current as a function of time. Very simple system and very sensitive as well. So after discovery of this one, we started to show some proof of principle studies, which was published in Biosensor Bioelectronics in 2016, where we showed that different molecules here, Varnase, Avidin, IgG, being detected by putting their appropriate marker on the surface. And here is another two, Streptavian and Barstar. These are actually negatively charged. So that's why the signal goes down when they bind. And these are all positively charged molecules. So signal goes up. And then you can, we also tried to see how low signal we can find. We have seen in back then in 2016 up to 200 picomolar for the concentration of avidin. One important thing is that it takes, as Jan also mentioned, very long time. Here you see the whole transient was about 1 hour or more than 1 hour, because they come to the surface by normal diffusion and it takes time. But that's not a problem, because when you want to know the concentration, you don't need to wait for the whole transient. You can simply look at the derivative here, because if the concentration is high, the signal rise faster. And what you see here is simply the derivative of that transient for avidin and IgG. So we make the surface specific by immobilizing antibodies, which is I have already described, so I skip that one. And then, as I mentioned, we have also developed this biofunctionalizing strategy with silk, which is already coated with these antibodies. So how specific is this detection? So in biology, the specificity is a very important term, and people conceive it in different ways. So for example, in this case, what you see here is that I have injected 10 nanomolar of IgG and 5 nanomolar of IgG, the solid lines, and then there are dotted lines. This dotted line means that then the surface had no antibodies. So basically they should not come and bind. There is nothing to bind. So they will simply flow and go away. But still there can be some signal because of the bulk effect, because when you inject molecules, it changes the bulk properties of the liquid. You still see some signal. But it disappears when you get rid of the molecule and put the buffer back. But this is only non-specific interaction. So it only tells you whether the molecule you are trying to detect can bind to the surface non-specifically. But in biology, we know that there are a lot of other molecules. So if you have an antibody, it can also bind to another protein, not the protein I'm looking for. And that's why we also have to do some cross affinity check. Here, the functionalization was done to detect IgG, but before injecting IgG, we sequentially injected HSA, human serum albumin, streptavidin, avidin, and then PBS, and then IgG. Avidin had some signal because avidin has a very strong, it's a very sticky protein, it sticks to any surface. But the nice thing about this technology is that this microfluidics are transparent. You can put fluorophore also with your antibodies or protein, and you can simultaneously detect optical signal when they bind and also electrical signal. But one thing struck us, and that is when I looked at the signal, I saw that the strongest signal came from IgG, which has isoelectric point 8.5, whereas the weakest among three was from Barnes, which has isoelectric point 10. Now, in my understanding, the process should depend on the charge. So here, this is more positively charged than this one. Then how come that this group gives the lower signal? And then if you look at the scale here the signal changes from almost 30 millivolt, where it is about 1 or 2 millivolt, although they are also very strongly negatively charged. So we wanted to understand why it happens. And we noted one interesting aspect of it. When I put them according to their molecular weight instead of isoelectric point, IgG is a massive molecule, 146 kilodalton in size, and Barnes is 27 kilodalton. I see there seems to be a dependence on the size of the molecule. Well, it was interesting and we wanted to check it further. So what we did, we took one IgG molecule. IgG looks like that, yeah. And this part, which is called Fc, is the binding epitope. So if you have the molecule antibodies, this Fc actually binds. The rest of the things do nothing. So they are simply to make the size bigger. So I asked my biotechnology friend, can you guys break it from here? So if you break it from here, I have only the Fc part. I still have the same binding, but the size is much smaller then. They said, yes, we can do that. So we got that one, and what you see the signal when I have 10 nanomolar Fc is a very small signal, whereas at the full molecule is a large signal. Well, so we were rather excited about that one. We thought, okay, let's do further investigation if that leads to something. And then we went to our blackboard and tried to understand from theory how does it look like. So we have the charge accumulation, we have the electric double layer for the sensor surface, we have the same for the molecules we are trying to detect. They also have the double layer and all this charge accumulation. Now, if we flow only on the sensor surface, it will accumulate charge, I'll see the current. But if we flow in presence of the molecule, there will be accumulation of positive ions, but if the particle here accumulate negative ions, that will also be accumulated. So it gives rise to some changes in the current, which we detect. But that only talks about the electrical influence on the signal. But then if you consider the particle when it is sitting on the surface, is actually also changing the local hydrodynamics, the way the liquid flows over it. So liquid will not flow over it like that, it will flow like that, which essentially changes the whole dynamics around the surface. So what it means is that now if you take a small protein and big protein, you are bound to see changes, right, in your signal. Now it was rather hard to find a theoretical foundation because it's a very complicated surface phenomenon. But we found one study where they said, well, if you want to analyze this complicated picture, you need to analyze from zeta I is the surface zeta potential of bare surface, then zeta P is the zeta potential of the molecule you want to detect, and there are some parameters like Ci and Cp which accounts for the influence coming from the charge and another coming from the size of it. And theta simply means the surface coverage. So if the theta increases, surface coverage increases, your signal increases. But if Ci, the influence of charge or influence of zeta potential, they also increases, you also see a change. Now we try to simulate that one. So we took a very simple example. We took a particle which has zeta potential 0. So basically then this term cancel out. So we have only this term, right? And what you see in this simulation is when the surface coverage increases, your signal increases, of course. But when your size, which is defined by AR is basically a normalized size. A is the radius of particle, and lambda is the Debye length, the screening length. So we are normalized with this one. Then you see that initially when the particle gets bigger, the signal gets larger, but then it saturates. Fine. And then we make it a little more complicated. So we say, okay, now let's assume that it also has the charge, and it also has all other properties normally biomolecule have. So here I have two examples. One is with size about 2, and another is size about 0.5, which is given the dotted lines. And then 3 different zeta potential, meaning that 3 different surface charge. One is minus charge, one is positive, one is 0. We see if the size is larger, the signal is larger, the red solid line. If the size is smaller, the signal is smaller. If the charge becomes from positive to 0, the signal drops. But if the charge becomes negative, signal actually gets inverted. Not only that, in that case, the solid line, which represents the bigger particle, induces a smaller signal. Now it brings us a bigger challenge. How do we experimentally verify these things? I mean, in theory, you can assume any charge, any size of any biomolecule. Nobody will prevent you. But if you want to have this kind of system, it's not so easy. But again, my biotechnology friends came to my rescue, and they said, well, we cannot exactly mimic the size and charge you want, but we can come very close to it. So they produced some Apurba molecules here, which has nearly neutral charge, but different sizes, which has opposite to the surface charge. So our surface is negative, so they have positive charge molecules, and they have of the same charge type. And then we can reproduce all we have seen in the theoretical simulation exactly the same way. We see that if the molecule is smaller, AR is smaller, the signal is almost close to our baseline here, and here the charge is also very small, close to 0. But if the molecule is slightly bigger, from 0.55 to 0.83, you see a huge jump here, although the zeta potential is very close to each other. But if you have also the zeta potential significantly higher than these guys, then you see even larger jump. And then if you have negatively charged particle, the signal inverts, and we almost have no dependence on the size. All right? Now I skip this one. What essentially means that if you select a molecule which has the right kind of property, your signal can be enormous. In this case, we took a molecule which is C1Q, is 5 nanometer average diameter, and compared to another molecule which is about 2 nanometer, you see the signal in this case, and compared to this case, the limit of detection was about 2 to 3 orders of magnitude difference. 2 to 3 orders. And that leads us to another interesting biological investigation. And I have to give you 1 minute description of what it is. This is basically our recent research. Extracellular vesicles. Have you heard of it before? No? You have heard of it, all right? Well, it has been seen that cell randomly emits some small biological particle. When I say small, it's about few tens of nanometer to few hundreds of nanometer. And for decades, people had no idea why cells are emitting those particles. So they thought when cell is about to die, they simply get rid of some material from their inside. But recently, they have found that these particles, what is known as extracellular vesicles, they are important participants in intercellular communication. Basically, cells design them in such a way that when they are emitted in the blood, they can track to the blood and find their target and give their all content to that cell. And this has enormous implication for disease diagnosis and therapy. Basically, your whole immune system you can actually sort of control by administering this kind of particle which can modulate the communication network. So this is a very hot topic in the research, and we got a big grant to understand the biology and function of these vesicles. But this is enormously complicated. Why? First of all, these vesicles are produced in different parts of the cell, and they have many different biological particles. So they may contain a wide variety of biological molecules. They have very different size. They have very different RNA content and so on. And as they are produced in different part of the cells, they also show different physiological properties. I mean, if you take some vesicles, they might be important for cancer, but some from the same cell, you might have vesicle which has no meaning. So it basically sort of give you a very challenging way to sort of decode their communication network. But anyway, as these extracellular vesicles are very interesting particle, we started to look at it because we have a sensor which actually gives stronger signal if the particle is bigger, right? We just have shown that one. So we thought, okay, let's try to profile them. So here our interest is to sort of profile their surface proteins. So if they have, like, let's say, for example, 10 different surface proteins, we want to check what is the abundance of the surface proteins, relative abundance between them. So we used our kinetic sensors. What you see is a lung cancer cell line where we analyze 3 different markers here, protein marker in this case, CD9, EGFR. EGFR is actually sort of lung cancer marker, and CD63. And this is an ovarian cancer cell line where we have tested HER2, HER3, and anti-CD3 protein. The beauty of this one is that as it is a microcapillary, it only requires 10 microliter of sample. It's very small. I mean, I got requests from doctors who are working with small children, neonatal, because the neonatal, they cannot give you milliliters of blood every now and then. So the doctors approached me, okay, can you use your technology to help us detect some marker, because our sensor can do it with 10 microliter and about in 2 hours of time. All right. So as I said, our interest is to understand the different level of expression of proteins on the surface. Here is an example. What we did in this case, this is not collected from body, but actually we have cells that we have engineered to produce 2 different expressions of the same protein. So EGFR is a protein expressed on the surface of the extracellular vesicles. So we engineered the cell so that they express less or more. And then we try to see if it is detectable by our sensor. And we see clear difference here. Another protein is CD63, where we also engineered the cell to produce 2 different types of protein expression. And finally, what you see here is a detection limit. What we can detect now is about 10 to the 8 EVs per milliliter. And we have miniaturized the whole thing in silicon chip, where you have 4 channels detecting 4 different markers. And what we are also working now, what we call a single vesicle fluorescence. Of course, you don't see it here, but here you see the small spots. These are 1 single vesicles, which we stained with fluorophore to measure their abundance on the surface. So you can change different fluorophore color to scan different proteins in this case. And my last slide, where I'm showing here atomic force microscopy imaging of these vesicles, because they are very small, few tens of nanometer, to make sort of profiling of their size. We want to know what kind of size distribution they have. And this is the ACM of those vesicles. I hope that I have been able to convince you that the kinetic sensor that we have developed, we have already applied it for protein analysis, exosomes, DNA, and some metabolites. And with that one, I try to conclude that this is a very nice sensor because it's very simple and it allows you to analyze a wide variety of biomolecules. It's sufficiently sensitive, and then it can be multiplexed to a high number. All right? So this is a small group we have. So half of them are situated in Uppsala University and half of them in KTH. Hitesh is responsible for fabrication. He is a clean room guy. He always stays in clean room, never comes out. And Federico is just left our group. He was a postdoc with me in Uppsala University who produced this single vesicle technology. Sarah is a PhD student who is responsible for extracellular vesicle analysis, whereas Siddharth is working with fundamentals of electrokinetic theory and application. Yupeng is a new PhD student who is developing single molecule FRET-based sensor, which I covered in my first talk. And we have a new PhD student, Fredrik, and Fredrik is responsible for single cell proteomics. So his research is about to analyze the whole protein content from a single cell. So we'd like to make an array so that a large number of cells can be scanned with the electronic sensor. And we have one more PhD position open for high throughput EV sensor and tons of master theses we always welcome. So please contact us. And thank you very much for your attention.
Thank you. Some questions? Yeah, please.
So I was wondering if electrokinetic analysis can be used in drug design. For example, after the drug interaction with the protein of not interest.
Yes?
If we can measure the concentration of binding sites that are remained.
Right. That's exactly what we do in this project. But we don't do it with protein, but we do it with vesicles. So here what we apply is that we take a lung cancer, what we are working now is that lung cancer patient, then we apply some drug to the patient and see the vesicles that are coming out of lung cancer, how their protein contents are modified. So it is not for drug development, but it's more for sort of monitoring the therapy response. But the same goes for drug development. If you have a sort of protein or molecules that you want to know their activity or sort of abundance, that can be used. Yes.
And the interaction with the lead compound, for example, in drug development with the protein, can you analyze it?
I'm sorry, once again?
The interaction between the drug, potential drug with the protein.
Yeah, so that analysis we do from the kinetics. So if we have a sort of conjugation like antibodies and protein, then if the activity is somehow different, the affinity will be affected. So we have a sort of code that can extract the affinity constant Kd, the dissociation constant, and if there is an activity issue, like your target has been degraded, then you'll clearly see that one affecting your Kd. Yeah?
Yeah, thank you. Some other questions? Yeah, please.
Which one?
Loader.
Learning chip is a very bright idea which can be fast and more cost effective, but as you mentioned, you have some difficulties with differentiation or different substances or proteins which you have in your analyte. Could you use some molecular techniques to increase this selectivity or
Yeah, selectivity is a very challenging issue, and selectivity comes quite much in the domain of biotechnology, how you prepare selective antibodies and selective capture probes. One possibility what widely is used is that instead of capturing with one antibody, because then you have this antibody which can also bind to other proteins. So you capture with that antibody, you get your protein here, but then you bring another antibody, right? On top of that, it's called sandwich immunoassay, and in that case, the selectivity can be much more improved. Yeah?
Okay. How many years it takes to come from the laboratory development of a sensor to the market?
It depends on the money and the demand.
I see. Okay. So because usually it's a long story.
Yes,
Usually.
but you know, in this kind of story cases, you need also some sort of how is it called? That the hospital needs to certify their applicability in the medical field, and that is very lengthy process.
I see. Okay, I know a story in Germany that they tried to push as fast as possible, and so when you go to a pharmacy and buy, you just sign that you take the risk.
Ah, okay.
Okay. Some other questions? No, then thank you so much. It was really very interesting. So would you like to continue?
No, I think I skipped that. I just wanted to comment that for these exosomes, we're collaborating with doctors at Karolinska Institute for Medical School. These are oncologists, cancer experts, but it happened to be lung cancer. And they will provide us with samples then. And we're starting now even from patients.
Yeah, but they are all dead patients, but we have their sample. The patient died during the investigation, but in all hospital they keep the patient's blood sample.
Yeah. So one interesting story, one interesting aspect is to see like during the progression of lung cancer, if the body produces more and more exosomes then, and if they give the patient a drug then like some chemotherapy or something like that, the number of exosomes will go down. So this is what we're trying to do now in this project. And then it's not as simple as we just detect one of these surface protein. Yeah. Probably we need to go for a multiplex sensing of maybe up to 10 different surface protein to be sure that this is an exosome coming from that cancer. So because different cancers then produce exosomes with completely different surface proteins. But lung cancer is just one alternative. I mean, it's like a general method. But first now, the first patient sample is not from the blood. It's taken from pleural effusions, which they actually take from lung cancer patients. It's like a biopsy. Well, they take from the body fluid
so pleural cavity, the lungs is in a cavity which actually help pumping. And then normally lungs also emit some liquids, and they are stored in that cavity. And in lung cancer patient, they actually emit more liquids which get stored in this cavity. And the advantage is that then you have more lung cancer related markers available there. If you take from the blood, it will have from the whole body, right? So it will need to do some screening. If you do from those cavity, it will be very specific or more abundant lung cancer marker.
Yeah, okay, so some other questions. Okay, then I would like just to say a few words, but it was really very, very interesting, and of course there is huge activities in this field. By the way, I want, since the whole world speaks about coronavirus, what is your actually opinion about the origin and the chances to overcome and to solve the problem?
That's a very difficult
question,
but also very, attractive. I mean, if I have the answer, I can go to the China and become a billionaire now.
Yeah. You see, this is like an introduction. You can find a link to the site of the KTH and the research groups that deal with this in Sweden. Since we have a direct contact to concrete professors from these fields, it is rather easy to get in touch to discuss different issues and so on. And I would like just to note that there will be also some possibilities just for visits, and it depends upon your interest, implication, of course, how you gain the experience in this field. I mean, you should be active here in Moldova, and I think that the field of biomedicine and the interaction with nanotechnology is really a huge field with, I'm sure, a bright future. You told about this kind of micro, let's say, robots, nanorobots, and so on, that can actually find cell, one cell, and repair it and so on. But of course this now looks fantastic, but I think you see, in 1990 internet looked fantastic. But now it's not fantastic, it's a reality. And of course in about 30 years the problem with the reparation of just one cell will be solved, for sure, will be solved. And of course it's important that people that really are, how to say, motivated and would like to contribute to the field, they can do this. But of course it's necessary to work very hard, to read a lot, to have the capability to understand what is important and actually what is not so important, because huge amount of information. You cannot read everything, you cannot absorb everything. It's very important that you just learn how to identify what is really important in the future for each of you. And taking into account, of course, all these issues, we wish you much success. And there will be new possibilities to attend courses, lectures of professors from other countries. So, would you like to add something to that? So,
yes,
please.
Just one little thing, that we can provide a PDF for our presentations here.
Yeah, that would be fine. That means PDF and will be uploaded on the
by email.
By email to all. Okay, and it will be possible also to upload the video registration to the portal of the project. That means each of you can come back and watch what happened here. And thank you so much, and thank you, professors Lindros and Dev, for your visit, for your lectures, and I hope that we will meet again in the future. We will have here schools, some working schools and so on, and we will continue this very interesting and useful discussion. So have a nice day. Thank you so much.